So now we've seen sequences, and given a sequence, I can talk about a series. So to define a series, we'll say here that a series is the sum of a sequence of numbers. Oops. And the notation we're going to use for such a series is the sum from k equals 1 to infinity of a sub k. Now, I put 1 to infinity, and again, these should just reflect the same bounds that we have on the sequence. So if I think of an example, we talked about our first sequence example in the previous video was the sequence with terms 1/2, 1/4, 1/8, etc. The associated series, instead of listing those terms, would add those terms. So 1/2 plus 1/4 plus 1/8 plus 1/16. And again, we had infinitely many terms, so I would reflect that by continuing that pattern. Again, I take that same general term, 1 over 2 to the k, and instead of putting it in curly brackets, when I'm talking about the series, I use sigma notation. So what we'd like to work toward in this video is the same idea with sequences, trying to figure out what we can mean when we're saying that a series converges versus diverges. So we're working our way toward that definition, and before we get there, I need to define something else related to series. So we see our series above, specifically in this example, has infinitely many terms. We can now refer to a related sum called the nth partial sum. So the nth partial sum of a series is the sum of its first n terms. So notation-wise, I'll use capital S sub n to refer to the nth partial sum. And we're saying it's the sum of the first n terms. So I have the same a sub k, but here I only sum from 1 to n. So that would be a1 plus a2 and so on, where we stop at a sub n. So if we go back to the example of the series we looked at prior to this definition, I can say that the nth partial sum of our series from 1 to infinity of 1 over 2 to the k, that nth partial sum would be defined as, of course, the sum from k equals 1 to n of 1 over 2 to the k, which we could write out as 1/2 plus 1/4 plus and so on, up to 1 over 2 raised to the nth power. Okay, so the significance of taking our infinite sum and now defining this nth partial sum is that the nth partial sum has finitely many terms. Series with finitely many terms are much easier to grasp and handle. You could think about, even if it had a lot of terms, if it has finitely many terms, it's feasible that I could think of finding the value of to which that sums. And then if I have an idea about the finite sum there, maybe I can build off of that to consider what happens is now I extend that to infinitely many terms. And this leads to the way that we're going to define convergence of infinite sums. So we're going to say that a series converges if its sequence of nth, sorry, I'm going to underline this, converges, if its sequence of nth partial sums, which that sequence I could express as curly brackets s sub n, I let n range from 1 to infinity, if this sequence converges. Otherwise, we say that the series diverges. So this is a very complicated definition, and I want to go through an example or a few examples in a moment to make sure that this hopefully has some meaning. So if you think about it here, we're trying to talk about convergence of a series, and in that definition, we refer to convergence of a sequence. So we have to recall there, how did we define convergence for a sequence? And what is that saying here? So this means that our sum from k equals 1 to infinity of a sub k converges if, we said the sequence of partial sums converges. And recall that that means that if we were to take the limit of the term of that sequence, so the limit as n goes to infinity of general term s sub n, which is the limit as n approaches infinity of our sum from k equals 1 to n of a sub k, this limit needs to exist and be finite. That's how we defined convergence for a sequence. So the sequence we have here is simply the sequence of partial sums. Now we can see from this bottom line why it makes sense that this would be related to the infinite series. We're taking the limit as n approaches infinity, and notice that n only appears up here. So if I were to send n to infinity, it makes sense that that would yield the infinite sum. Now what we're going to see in practice is that if I can find a way to express the nth partial sum in some nice form as a function of n, then taking that limit, just as we normally take limits, would allow me to decide if I do have a series that converges or not. The other thing we're going to see is that often finding such a nice form for the nth partial sum is not easy to do. And this is going to mean that we will develop some tests, as we call them, for convergence and or divergence that we hope we can apply to certain series. That all of these tests are dependent upon this definition of convergence or divergence, but hopefully they provide us with ways that we can check that convergence or divergence that doesn't involve taking this limit of the partial sum. But that is in future lecture videos. So while we are looking at this definition, let's think about it with some examples. And in particular, what I think can certainly be confusing is distinguishing between the sequence of terms, a sub k, and this new sequence of partial sums. So what I'd like to really point out in these examples is the difference between those two sequences. So consider, a sum from k equals 1 to infinity of some a sub k, where I'm going to define a sub k in the following way. I'm going to give it a piecewise definition. It's going to take on the value k when our index k sits between 1 and 5, and then it will be 0. So suppose we wanted to look at this series, which is the sum of the a sub k's. I want to distinguish between two things. So we can talk about the sequence of the general term a sub k. That sequence, to be clear, would be the one whose terms are 1, 2, 3, 4, 5, 0, 0, 0, and then it would be zeros indefinitely. So that's what the sequence of the a sub k's would look like. We could certainly look at that and say that the limit of a sub k is 0, right? If I look at that pattern there, that's going to be 0 ever after. So that limit exists and is finite. So this would tell me that the sequence a sub k converges by definition to 0. So importantly, this really tells me nothing about whether or not the series converges based off of how we've defined this above. So this is a completely different question. This tells us nothing about whether the series converges. in order to look at that, if you look back at our definition of convergence for a series, I see that I need to construct a different sequence, and that is the sequence of partial sums. So we can come back and consider that sequence and write out the terms here. So this is, again, from n equals 1 to infinity. So the first term, s sub 1, is the sum of the first one term of this series, so 1. Then s sub 2 would be the sum of the first two terms. That's 1 plus 2, so that would give me 3. S3 would be the sum of the first three terms, so 1 plus 2 plus 3 is 6. The sum of the first four terms is 10. The sum of the first five terms is 15. And then beyond that, as I add on the next term is always going to be 0. So this one would continue to have terms 15. And so this would be what the sequence of partial sums looks like for this particular series. So if I want to decide if that sequence of partial sums converges, then we take the limit as n approaches infinity of s sub n, the general term of the sequence. And notice that this levels off at 15 indefinitely, so I can see that that limit would be 15. Again, importantly, that limit exists and is finite. So what that means is that the series converges, and it converges to the value 15. And that's using the definition to establish that. I'll also point out here a consequence of convergence for a series is that if I say that a series converges to a given value, that means that the series sums to that number. So here we could say the sum of the series is 15. But I do want to point out that it's important here that the definition of convergence is not the series sums to a finite number, because that definition gives me no idea of how I would actually verify that. Instead, our definition is carefully crafted so that we could actually check it to determine whether or not a series satisfies that. And then let's look at one more example, again, focused on distinguishing between these different kinds of sequences associated to a series. So here, again, I want to consider the infinite sum of a sub k, but I'm going to define a sub k not as piecewise, but as minus 1 to the k. So this is the third example we saw when we looked at what a sequence was before. And in particular, we actually have seen this sequence of terms listed out. So actually, let me write this as a sub k. So when I talk about the sequence, here a sub k, as we saw previously, that is the sequence with terms minus 1, 1, minus 1, 1, and so on. And we've already established that because the limit as k approaches infinity of a sub k does not exist, the sequence with terms a sub k diverges. Again, if I want to consider instead what happens to the series, we want to look at the sequence of partial sums, which I can, again, list out exactly what that sequence would be. The first term would be the first term of the series, which is minus 1. The second term would be the sum of the first two terms. Minus 1 plus 1 is 0. The sum of the first three terms is minus 1. The sum of the first four terms is 0, and we get this pattern that we can see is going to continue indefinitely. So it's this sequence that I want to study in order to decide if the series converges or not. So again, I come back and think about the limit as n approaches infinity of s sub n with my general term here. And again, looking at the terms of this sequence, I can see that the limit does not exist. So this is a different sequence than that of a sub k that I listed above, but it has the same problem that it's always oscillating between two values. So because the limit of this sequence does not exist, that means that the series that we started with here diverges. And again, this is by definition. We've shown that the limit of its partial sums does not approach a finite limit, and consequently, that's how we define the notion of divergence for a series.